In this session, we are going to mostly concentrate on the implementation details of our processor. So far what we have studied is primarily the theoretical details of the different components that has to be there in the computer, rather in the processor. And we have looked into the details of the construction of the arithmetic and logical unit first. We started with that is the ALU. After that, we have looked into the registers and the common bus architecture, that how does these registers copy data to another register or to and from memory, right? And after that, we have also looked into the different bits that are going to control these different components like registers or ALU or the program counter and so on, using the control logic, right? And alongside with these three things, we have also looked into a few specific registers that are needed, or like rather special purpose registers that are needed in the processor. So the registers A, B and C that we had been talking about for so long were the CPU general purpose registers that could be used by a programmer to store data or manipulate data, right? So that could be used as a part of the software that you develop. But there are some special purpose registers which are not really used from a software standpoint. They are typically used for controlling the flow of the program, and they are whatever we have already discussed was the program counter is for keeping track of the um, uh, instructions address, right? The one was program counter, the other one was the instruction register, where if you remember, we were copying the data from the memory to the instruction register, and then there was this memory address register. So I'll just quickly classify them. So apart from we have general purpose registers, general purpose registers. We have went over this many times, so this is primarily a summary and you should be able to recall them, right? So we had in our implementation register A, B and C. Out of them, A and B was directly connected to the ALU. Okay, for any computation that needs to be done on the ALU, A and B has to be loaded with the relevant values. C is not directly connected to the ALU. Okay, so keep this thing in mind. And this is not again a hard and fast rule or anything fundamental. This is how we have designed our CPU. You can come up with any other design. Okay, but in the context of an implementation, we have to be very specific about what we want to do. Okay, so in our example, we have made this specification that although A, B and C do have connection to the main bus, ALU can also output to the main bus, but the ALU only takes inputs from these two registers A and B, and we have referred to A also as an accumulator. So register A or an accumulator, register B and register C, these are the three general purpose registers. So apart from that, we had special purpose registers. Although technically program counter is like a counter, right? I'll still mention this to have all the components in the same bucket, right? So there is this program counter. This is, I would say, rather a counter. Okay, so this is going to count or this is going to be serving as a pointer to the address of the next instruction that is going to be executed. Okay, we again went over it many times, and we have also designed control words. So one of the things that you should directly remember is that how a program instruction is fetched. How does a instruction get fetched? The program counter has the address of the instruction to be fetched, right? So what happens is the program counter outputs this value to the bus, which is loaded into the memory address register. Okay, or MAR. So this is a special purpose register, and note that the size of the register is going to be equal to the size of the addressable memory. So in our case, we were addressing a memory of size only 16 bytes. So the length or the size of this memory address register was 4. Okay, similarly the program counter is a 4-bit counter. So these are not data really, this is primarily all the address related information. So these are all 4 bits in our implementation. Okay, so memory address register again directly talks to the memory, and the memory could be enabled or disabled based on whether you want to read from the memory or write to the memory and so on, or you want to make the memory completely inactive, not interact with the address the data bus, right, or the common bus. Then there is one more thing that we kind of did not have it in our system, but we kind of mentioned that somehow. So we have made this assumption that memory, of course, the memory has permissions for input output. So you want to either write to the memory, or if you want to read from the memory. So these are like the control inputs, right? So I mean, these are all inputs, these are controls, right? And based on that, you are going to have something to read from the memory or write to the memory. And you also have this common bus. Okay, so this is a common bus. This is one implementation that we have gone forward with, right? But in many of the realistic implementations, the memory do not directly write to the common bus. Rather, we have a dedicated CPU register, and the CPU register is integrated or interfaced with the common bus. Okay, and that could be primarily due to the reason because the memory could be a slower device, the memory needs to be ready, it might take multiple clock cycles for doing that, right? So instead we also use another special purpose register, which is called the data register or memory data register. So this is called memory data register or memory buffer, MBR, MDR, right? There are many terminologies. So the reads and writes are going to happen like this. Okay, and also this has control lines, which in turn is interfaced with the common bus. Okay, so the memory is going to be interfaced to the common bus via the special purpose register called a memory data register or memory buffer register. So I have not used it explicitly in our design, rather we have directly used this link. We have directly interfaced this with the memory, but of course you have this thing, right? You can always use this MDR. So memory data register or MDR. Note that this has nothing to do with the address, right? So this is the data that is going to be loaded from the memory to the common bus to wherever it wants to be transported to. So this is an 8-bit register. This is actually the size of the data that is stored in memory. Okay, so this is something we were ignoring in our current implementation, but from a theoretical standpoint, you should know that there is this register which is also going to play a role so in the processor design. So now there is one more step that is left to finish the fetch cycle. So after the memory address register gets loaded, it looks up the appropriate instruction from memory. The memory is going to output the data to the common bus, the data here being the instruction, and that data is loaded in the instruction register. So there is this instruction register. Okay, so the instruction register here we were assuming it to contain only the instruction, right? Although it can contain both instruction data, we did not go into that debate because for us the instructions are quite simple. So we can just assume that this is just 8 bits. It is the entire instruction that is going to be executed. It is going to contain both the opcode as well as the as well as the operand. So in case your operand or in case your instruction is like a jump instruction, right? So the jump instruction is going to look into the operand, because the value of the operand is the address by which the program counter needs to be loaded, right? So if you have, I think we have discussed it in the last class where we discussed about JMP or JNZ. So if you have JMP, let's say 0x3, right? If you have like 0x3, and if the jump instructions opcode is, let's say, 6, right? So 0 1 1 0 and 3 is 0 0 1 1. So your machine code reads like this, right? 0x63, right? So your instruction register is going to be loaded by this value 63, right? I mean in hexadecimal. So your IR instruction register is going to contain these two parts, 6 and 3, and 6 is something that is interesting for the control, because the control logic needs to know that this is a jump instruction, and this 3 goes to the data bus, right? And this has to be going to the program counter, right? The program counter is going to load the value, is going to be loaded with the value 3. Maybe it was at 7, right? Maybe the PC was at 7, and once it goes to 8, the program tells that no, don't go to 8, please go back to 3. Okay, so this is a program counter load. So this is going to be the value by which this program counter is going to be loaded. So this is an address. This is the opcode that goes to the control. Okay, whether it is jumping to 3 or whether it is jumping to 35, the control does not have any business with that. It just says that the next instruction, the next control should be, the program counter should be loaded from the output of the instruction register, right? In our case, the last 4 bits or the least significant 4 bits of the instruction register is the value by which the program counter should be loaded, and you should allow the program counter not to do a regular increment but to update its current count value to 3. So that is the job of the control logic. Okay. So instruction register is, we have seen. We will also see a special circuit called the instruction. It's not a register, instruction decoder. Often we want to enumerate which instruction we are trying to execute, and maybe there are some ALU inputs that we will be using to indicate the ALU that which instruction is getting executed. It's not just the control, but the ALU, as I told you, will also need some inputs to decide what operation it is going to do. So that is the reason we might have the instruction decoder. In a small block diagram, I am going to show you here. Let's say this is your ALU. This is your ALU, and the ALU is going to have some functionalities, right? Addition, subtraction, some logical operation, blah blah blah, right? And he is going to have some outputs and inputs. So there will be some input from these 2 registers A and B, at least 1 register, at most 2 registers A and B. Again, in our case, there could be 3 registers also, right? There could be source 1, source 2, destination 1. Right. So here we were assuming this only 2, A and B, and in most of the cases the result was again written back to A. So the result output is written back to A, and here you actually have some bits that are dedicated to the type of operation. Okay. So this operation is typically indicated by, it could be indicated by the instruction decoder, right? So this is one way, right? Or you can directly take some bits of the instruction and say that the ALU can understand what is the instruction that has to be executed. So something from the instruction decoder could be potentially fed in here to indicate what operation is going to be executed. Let's say we want to execute, in our case, the ALU does subtraction or addition. So our opcode for addition was 3 and the opcode for subtraction was 4. So there are definitely two different lines that are going to be activated if in through the instruction decoder, and we can feed that to the ALU to indicate that you have to do an addition or you have to do a subtraction. If you have more number of bits, you can also indicate that, right? If you have more number of operations, let's say if you have 4 operations in the ALU, addition, subtraction, let's say or and not, right? So you should use 2 bits to indicate that, and those 2 bits will come from the instruction decoder, right? So here we just discussed the special purpose registers and some extra things like the program counter and the instruction decoder, and these are the general purpose registers, right? And apart from this, we had the ALU and the control unit. Okay, so now we are going to look into the implementation details of them one by one, and also try to see how these are all put together, and we can run something like a very simple program, right? We will start with a very simple program and see that how this is getting executed. Okay, so let us go to the implementation first, right, and see that what program is we are trying to execute, right? So let us go to this part. So this is our CPU, right? I have kind of introduced you to this earlier, so you already have seen this picture several times by now, and again kind of revisiting the fact that what are the different components here. So this is your register A, this is your register B, whatever turns yellow is something that I am describing. This is register C, this is the ALU, right? This is a status register, and you have a display that is connected to register C, right? So I may want to transfer the content of the accumulator to register C, and if the content is in register C, I can directly see this output. Okay, so if I am putting something in register C, the value is going to be visible, and that is implemented by using the out instruction. Okay, so I think here I have modified this, right? This is currently showing that 7 is swap, but 7 earlier it was something called out, out, right? Out is going to show the content, right? So currently ignore the statement or ignore the instruction called swap. Rather than swap, you can think of this as just moving the data from the accumulator to C, right? That is going to show you the content of C. Swap basically is not only A to C but also simultaneously C to A. That's why it became swap. But swap still it does still the same thing, right? Just that C and A is not swapped. A is only transferred to C, and the value is displayed on the these LEDs, right? So there are two 7-segment LEDs. Each 7-segment LED is going to indicate only an output for 4 bits, but as you can understand that these registers are 8-bit long, right? So there are two 4 bits. So the left one is the most significant 4 bits, the right one is the least significant 4 bits. Okay, so the right part of the figure is over. Now coming to this is the common bus. So this long wire that you can see in between from the top to the bottom is the common bus, and as you can see, every component that needs to interact with each other, they interact via the common bus, except some special cases. For example, the register A is directly connected to the ALU, register B is directly connected to the ALU. I think we discussed this thing earlier. Or the memory address register is directly connected to the memory, right? The out of the memory address register, this line, as you can see, memory address register out is directly connected to the memory, right? ROM here, right? Ideally it should not be a ROM, it should be a RAM, but here I have shown the circuit component ROM because you can nicely see the contents of the ROM very nicely, right? The RAM in this particular simulator doesn't show you what is the content at that point in time, right? So there is no real difference as far as our simulation goes, just that there is one bottleneck, that because it is a read-only memory, you will not be allowed to write to the memory, you can only read from the memory. Okay, but for us maybe that is enough to do a simple demo, right? So we don't want to write to the memory, we'll just read the program, read the data, and whatever it needs to be displayed, we can display it in the output, because we already have an output, we are not writing back anything to the memory. Okay, and whatever computation we are going to do, we can only use 3 registers A, B and C, nothing more than that. You cannot have a temporary memory to write back the data in case you run out of registers. Typically that is the case, right? Suppose you have 10 registers and you want to store something extra that is required by the program, but you cannot really fit in those 10 registers. You have to unfortunately go and write it back to memory and fetch it whenever it is needed. Okay, so keep that in mind. We will not be able to write back anything, although we have an instruction called store accumulator, which is supposed to store the content of the accumulator back in memory, but we will not be able to do that with this component. Although we have the instruction, the control signals will all be generated if you want to execute that. Unfortunately, the store part will not work. Okay, but that does not conceptually change anything. Okay, so now let us concentrate on the left hand side. I spoke about these 4 things: program counter, memory address register, instruction register, and instruction decoder, and of course this memory, right? So instruction register, as you can see, is here. The instruction register has these 2 things. One is going out towards the instruction decoder. Instruction decoder can see, there is a single output called subtraction. So if the subtraction is set to 0, it means that you have to do addition, and if subtraction is set to 1, the ALU will understand that it has to do actual subtraction. So this subtraction output, as you can see, goes to the ALU. So this is the subtraction line, right? So this is the subtraction line, it directly goes to this input of the ALU called AS. AS means add subtract. So if AS equal to 0, this means addition. If AS equal to 1, it means subtraction. Okay, so and you have already know that how this is done. So we were taking A as it is, and if AS equal to 1, this we will do B XOR 1, which is basically going to be B complement, and if AS equal to 0, B XOR 0 will be B. So it doesn't matter, and the carry in of the full adder is also going to be AS. If AS equal to 0, then you practically do A plus B. If you have AS equal to 1, then you do A plus B bar plus 1. So A plus 2's complement of B, which is going to be implementing A minus B. Okay, so there is nothing much there on the right hand side. So the other most important part here is this, right, which is the instruction register is also going to give out the instruction to the control logic. So this is the control logic for our CPU. So on the right hand side of this chip, right, you can see the different control bits going out, starting from program counter increment. So if you follow from PC, INC, PCO, this is our first output, second output, third output, dot 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 up to the 16th output. So REG ALU 0 is our probably our 16th output, or the 15th output rather, because we were having 15 different lines, and one was, I think, dummy. So we have to check back, right? So register C out is not used here as far as I can understand. This is, but you can always, depending on what kind of micro instruction you are using, you can check that. Okay, so now coming to the execution of a program, we have to write the program in machine code, right? There is no assembly code also possible here, because I do not have an assembler that takes your assembly level code and converts that into machine code. That is not possible. So of course, I mean, that's possible. You have to write a assembler for that, which could be a very simple program in our case. Okay, that could be written in Python, for example. Somebody writes a code like the ones I have shown you earlier, LDA something, add something, sub something, and that is going to be an input to the assembler program, and the assembler is going to create the machine level code. Okay, so here I have written some program, and the syntax is going to follow this instruction opcodes, right? So we have here 1, 2, 3, 4, 5, 6, 7, 8 instructions. The last one you can assume this as a out instruction, but we are not using it directly here. 7 in our case is out. Yeah, we are using it, but the swap feature is not being used. It's primarily being used for display. So NOP does nothing, right? It's simply going to wait on that clock cycle, and then whenever the instruction cycle is done, it is going to go and load the next instruction and so on. 0001, which is basically hexadecimal 1, right, does the load accumulator from an address. Okay, so it is going to look up a particular memory location which is specified by the instruction. So it is going to be LDA some address, right, LDA 7. So LDA 7 is going to be hexadecimal 17. So 7 is going to be referred, so 7 is the pointer. It is going to be referred to the memory location 7. Whatever data is available in the 7th location, that data is going to be loaded in the accumulator. That is called load, right? And the other one is a store. This is like a load store architecture. So you have load instruction and store instructions, and this is the storing and loading directly by the address. So store is going to be the exact opposite. If you say store some memory location 7, which is going to be indicated by in the hexadecimal machine code 2727, 2 stands for STA, 7 stands for the memory location. Okay, what will happen? The accumulator has some data. Let's say the data is some hexadecimal 35. 35 is going to be written to the memory location 7. Okay, so that is what is meant by STA, like store accumulator, store the accumulator at a certain address. Then we have add, subtract. We have discussed about it n number of times. Add means you will basically be using add address. So the accumulator content is going to be incremented by the value at that address. So if your accumulator is containing 5 and you say add 7, and the memory location 7, let's say, contain 3, so the value is going to be 7. 7's value is going to be 3. So 5 plus 3, 8. Similarly, sub, LDI, and jump we have discussed. So now, given this machine code, right, we have tried writing a program, right, and this program is already loaded in our ROM. Okay, so let us see what this program means, right. So we have so this is a ROM that starts from the 0th location. This is the 0th location, the dark green. This is the first location, this is the second location, third location, fourth location, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, and 15th. Okay, so 10th, right, 10th is going to be A, right. So if it's 0, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is going to be A in hexadecimal. So this memory location should be referred as A. This is B, this is C, this is D, this is E, this is F. The value that is stored is something that you can see. So if I ask you that what is the value that is stored in memory location F, what will be the answer? The answer is going to be 0, 0. If I ask you what is the value that is stored in memory location 2, okay. So if you look at, this is 0, this is 1, this is 2. So 2 contains the value 70. 3 contains the value 3C. 4 contains the value 70. 5 contains the value 4D. 6 contains the value 70. 7 contains the value 4E, and so on. Okay. And one more thing we have to keep in our mind, that the memory that we are using is used for both program as well as data. Okay, so I do not have any separate program memory and data memory. The program that is going to be executed in our computer resides in the same memory wherever the data resides. Okay, so you have to kind of coexist in the same memory space. Right, you can also have advanced architectures where they are not the same and so on, but in this particular example architecture that I am showing you, they are the same. Okay, now let us look at the program. The program starts from the first memory location 00, okay, and runs through this. So I have a program. If I ask you the size of the program in terms of bytes, the program takes here 9 bytes. Okay, 1A, 3B, 703C, 704D, 704E, 70. So this is the total length of this program is 9 bytes, 1 2 3 4 5 6 7 8 9. After that, this is not the program, but I could use these areas or is this memory location as data. Okay, so now let us try to understand what it means. What is 1A? 1 stands for load accumulator with an address. So if you are you have forgotten, you can just go back here and you can see 1 means LDA. So it is going to be LDA. I am using 1, 3 and 4. So 1 is LDA, keep in your mind, 3 is add, 4 is subtract. Okay, and 7 we are also using 7 0. If you see 7 is display. For now you can simply assume that 7 is going to display the content of the accumulator. So it is going to transfer A to C and show the value in the LEDs. Okay. So now coming back, let us try to understand what this program is going to do. So 1A is LDA-A, right? So LDA-A is going to load the value of the memory location A into the accumulator. So one will ask the question, what is the value in the memory location A? The value in the memory location A is 5. So this was A, right? So if I execute this instruction 1A, we are going to see that 5 is loaded in the accumulator. We can try this out and see that what is going on, how it is done. Okay, so for that what we have to do is we have to reset the system and then do a clock by clock analysis and see what is going on. Okay, so let us, there is a system reset. The system reset does nothing but it basically sets the program counter as well as the t state counter value to 0. That's all. Okay, so I have reset the system now. Now if I put one clock pulse, right, something will happen, right? So let us first concentrate on the control logic. Okay, so this is the initial, you have just booted the computer. This computer is completely reset. If the computer is reset, the program counter, as I told you, is set to 0. Program counter is set to 0. The t state counter is also set to 0, right? And we have to now issue the control because the computer has to now proceed. What will the computer do? Computer doesn't know what to do, right? The control will tell that, okay, you are at t state 0, doesn't matter, whatever be the instruction, you should be executing the fetch cycle, and the fetch cycle basically means the program counter should be outputting and the memory address register should be inputting. So let us see what the control logic is doing for us. So if you look at the lines of the control logic, the light green basically refers to 1. So program counter out is activated, as you can very easily see, right? And memory address register in is activated. That is also something that you can very easily see. Okay, so MAR in and PC out are activated, right? So after executing this, what will happen? The memory address register is going to contain the value 0. Okay, so if I put one more clock, the memory address register is going to contain the 0. You can see this memory address register, it has an out, it is loaded with 0. The value is 0, so the ROM is pointing to the value 0. After this clock, there will be two things. One is transferring the data from the memory to instruction register. So memory output, now you can see it is high. Instruction register in is high. So whatever is going to come out to the common bus, right, after this control signal is executed in the next clock pulse, you are going to see that data in the bus, and at the same time one more thing is done, is program counter is incremented. So the program counter is now going to start pointing at 1 instead of 0. The next instruction is going to be executed. Okay, so let us try this out. I'll give one more clock pulse. So now as you can see, the bus has this value 1A because the memory is outputting the value 1A to the bus, right, with this control signal. And after this, we put the clock cycle, the instruction register is also going to be updated with this value. Okay, so now the instruction, you cannot see this, maybe you can partially see this, right? Here 1 is basically going to refer to the opcode. So 1A, right? So 1 is the opcode part and A is the address part, right? And the bus contains, as you can see, 1A. Okay. So here, as you can see, the memory location is being referred is 5 because that is the 8th location, and here memory address register in is high and IR out is high. So IR is basically going to say that please load the content of value A, right, content of memory location A in the accumulator. Okay. So after this, this is going to go up, right, register A in. So first we are now loading from the instruction register out to the memory register, memory address register. So if I give this instruction, this is now loaded, and now the bus contains the value 5. Very carefully see. So now at location A, memory address register is loaded with A, right? So A is now being issued to the memory, right, which basically says that memory out, right, this is memory out now, and register A in. So memory out and register A in. So memory is now outputting, so the bus contains the value 5 and accumulator should also contain the value 5. Okay, so you cannot see the content of the accumulator directly, only whenever there is an output you can see that. Okay, so I can put one more clock pulse. Now you can see 5 is there in the accumulator. Okay, so all the lines have become red because at this point of time nobody else is writing any control signal. So all the control signals are now revoked, right? All the control signals have become 0. That basically means nobody is, the bus is in a high impedance state. Nobody is trying to read from the bus, nobody is trying to rewrite to the bus. So this is what we, in the simulator, they show it as this red color. But all the things that we wanted is done, right? The accumulator contains the value 5 and that was what was expected. Okay. This is how an instruction gets executed. So now you may think that the program counter is going to be updated by the value, the new address is going to be 1, right? Because 0 has been done and we have incremented it in the second micro instruction. So now the PC, if I execute the redundant cycles now, because if you remember, if you are using a counter that counts from 0 to 5 or 0 to 6, right, I am only going to use the micro instructions that are useful for this instruction. The rest of the micro instructions will be just simply a 0, right, because I have not done an intelligent counter that resets once the useful micro instructions get executed. Okay, so if it is a 3-bit counter, I am counting from 0 to 7, and if only the first 3 micro instructions are important, so 0, 1 and 2, after it is done, the useful work is completed. So 4, 5, 6, 7, whatever, right, those will be just NOP kind of a thing. It is just going to be zeros. So here also we will have the same thing. Even if I give a clock pulse, you can see none of the LEDs are glowing. All the outputs of the control are 0. There is nothing happening in the computer. It is basically wasting clock cycles. Okay, so I'll put one more clock. Now I see some control, right, and this control is basically trying to load the next instruction. So PC out is again up. PC out is basically going to load. See, the bus contains the value 1. Why? Because now the address of the instruction that is going to be executed is 1. So the bus contains the value 1. Okay, bus contains the value 1, and this is going to be again loaded into the memory, memory address register. Okay, so you will see that is what is going to happen. So it's the same kind of a process, and let us try to see what is this instruction and try to understand this instruction. So this instruction is 3B. Okay, so 3, if you remember, was addition. Add is 0, 0, 1, 1, and 3B is what? B is the location of the memory. So what does B contain? B contains the value 3, because A was 5, B is 3. What will this do? This is going to add 3 to the content of the accumulator. So the accumulator contains how much now? 5, because I have done LDA A, right? LDA A loaded the accumulator with the value 5. Now I am doing 3B. 3B is adding 3 to 5. So the accumulator is going to contain the value 8. Okay. So let us run through the process of 3B, right? How this 3B gets executed. So we have fetched the instruction, done, right? The instruction, so 3B is there in the bus. So the instruction is already there in the bus. The instruction register is going to be loaded by that. So let us load it. We have loaded the instruction. Now, as you can see, the instruction register output is 3. So the control needs to know it is an add instruction, right? So 3 is, you can see very easily 3. So 3 is going to be communicated to the control logic, right? So as you can see, this line, the blue line you can follow, this actually goes to the control. Okay, so the controller knows that this is an add. So I have to be careful what I'll do. Okay, so 3 is there in the instruction register. What will this do? This is going to now look up this memory location B, right? The B is an address. Okay, so I'll do one more clock. So if I do one more clock, you can see that MAR in and IR out. IR out means IR's output, which is basically 3B, and MAR is only going to consider the last 4 bits of 3B, which is B, right? And as you can see, this 3 is basically being referred, right? What is 3? 3 is the value at memory location B. Okay, so what will be the next thing that is going to be done? This value 3 is going to be loaded to which register? Register B, because A plus B has to be performed. Okay, so if I give one more clock pulse, right, you can see very easily, it's interesting to see, memory out, register B in, right? These are the two light green colors. So memory out is memory is trying to write whatever is this the value. So this value is 3, right? Don't confuse it with 3B. 3 is the value here at memory location B. Okay, so 3 is basically output to the bus, and who will take this output? The register B. So if I give a pulse, you can actually see that 3 is loaded here. Okay, so 3 is loaded in B, 5 is loaded in A, right? So the ALU, I can assume that it contains the value 8 now, because the combinational circuit, right? So in the next clock pulse, what I will do, or what the controller will do, the ALU will be given the ticket to write the data in the bus, and register A is going to read that. Okay, so if I give a clock pulse, 8 is going to come out to the bus and will be written to where? It will be written to register A, right? So very clearly the game is now just here. Accumulator contains 5, register B contains 3, ALU internally contains 8, is supposed to contain, otherwise there is some problem, right? And AS, as you can see, is 0. It's not a subtract operation. If it was a subtract operation, then it would be 5 minus 3, right? But it is 5 plus 3 now, because AS equal to 0. Okay, it is an add operation. So let us give the clock pulse and see what happens. So if I issue a clock pulse, you can see the output. So ALU out is high, register ALU out is high, register A in is high, rest of them are 0. Okay, so you can see that the ALU now contains the value 8. Okay, this was our expected answer, because 5 plus 3 is 8, right? And the accumulator contains the value 8. So if you see the next instruction, which is 70, 70 is, I told you, 70 is simply going to transfer the value of the accumulator to register C, and if there is something in register C, the register C dumbly shows that. right? There is no control that I have made any specific control. In this particular implementation that I am currently showing, if I issue this command 70, A's value, which is 8, is going to be loaded in the register C and is going to be displayed. So let us try that. Of course, you have to do fetch, right? Doesn't matter how simple the instruction is, you still have to do the fetch. Otherwise, the CPU will not know what exactly it has to do. So let us go through the regular fetch cycle. After this fetch cycle is done, register C in, you can see this register transfer very clearly here. Register A out, register C in. That means that register A is basically being transferred, the content of register A is being transferred to register C. Okay. So if I give the pulse, that is what is going to happen. And now you can see that the register C contains output. Your answer is 8. 5 plus 3 is 8. Your computer is actually executing this code and telling the answer, right? Although 5 plus 3 is extremely trivial for any one of you, but this is something which is done in software, and a computer performs 5 plus 3 in this way. Okay, so you have to have instructions that are executed one by one, and 5 plus 3 is now executed and displayed. I had some very toyish display function. That is what is getting executed and being displayed. Let us now proceed, right? So we have 3C. What is 3C? Again an addition, right? So we had loaded it with 5, then we added 3, it became 8. Then we displayed, it became 8. Like, display is not going to change anything, right? So this is accumulator still contains 8. 3C, 3 means add, C is, I am going to look at the content of the memory location C. C contains the value A. Okay, if you are not comfortable with hexadecimal, A is 10, right? So if you have a value 8 in the accumulator, and if you add 10 to that, it becomes 18 in decimal, right? 18 in hexadecimal is 12, right? Why 12? 1 into 16 plus 2. It's actually in hexadecimal 12 is equivalent to hexadecimal 18. Okay, 16 plus 2, 16 into 1. Basically 16, 1 into 16 to the power 1 plus 2 into 16 to the power 0. This basically becomes 18. So after you execute 3C, the accumulator, and 3C followed by 70, then the accumulator is going to contain the value 18, decimal 18, or it is going to display the value 12, 12, because it is hexadecimal. What can we do? We have to display that in hexadecimal form. We are doing this bit by bit comparison, like bit by bit, like 4 bits converted to hexadecimal value. So let us execute that, right? I put one more clock pulse. I'll basically skipping these clock pulses very quickly. So now, as you can see, the 3C is in the bus, right? So the the register B is going to be loaded by the value A, right? So now bus contains the value A. This is going to be loaded to register B. So now if you see, let us go to the right hand side. Register B contains the value A, right? Now the game is set up again. The register, the top register, register A or the accumulator is containing the value 8. Register B is containing the value A. So 8 plus A is 8 plus 10, that is 18. So let us try to run the computation one more time. Basically the computation is done, probably is definitely done, because 8 and A are there in the registers, and it is directly connected to the combinational circuit, which is the ALU. So we just want to wait for the data to be transferred from from the ALU to the output bus, and from the output bus to A. So if we just execute that, you can see the value 12 coming here. And this is just a debug thing, right? But there's no real display here. I'm just debugging because that is a feature given by the circuit simulator. I will try to transfer the value of A to C and then display that to you. So in the next instruction, I have 70. So yeah, so now that instruction has been executed. So now I have the value 12, which is 18 in decimal. So I have done 5 plus 3 plus 10, okay, and displayed it. So this is not just some 2-digit addition, but we were actually adding more than 2 numbers, right? So 5 plus 3, then I added one more number, and we will continue like this. So I have a long example. So 5 plus 3, then display, then 3C was adding. Now the value in the accumulator is 12 or 18. Then I have 4D. Okay, what is 4D? 4 means subtraction, right? 4 is going to be in subtraction. You can check one more time. Add is 3, 4 is subtract. Okay, so if there is anything called 4, the processor knows that I need to subtract. Remember that there is no difference in between addition and subtraction in terms of control. So now the interesting thing would be that AS is going to be set to 1 using the instruction decoder. How it is being done, I will show. So 4D, let us try to understand what will happen. D contains the value 6, right? A is 5, B is 3, C is A, D is 6. Okay, so 6 is going to be subtracted from the accumulator. How much does this accumulator contain now? The accumulator contains 18. 18 minus 6 is how much? 12 in decimal form. What is the value of 12 in hexadecimal form? C, right? So if I execute 4D, the content of the accumulator is going to be C. Then there is a display, then there is a 4E. What is 4E? E contains the value 4, right? So if I execute 4D, the output is going in the content of the accumulator is going to be C. If I execute 4E, so C minus 4, what is C? C is 12. 12 minus 4 is basically 8, right? So once you have executed 4E and displayed the result, this is going to, the final result is going to be how much? 8, right? So what effectively you are doing is 5 plus 3 plus 10 minus 6 minus 4. So minus 6 and minus 4 is like minus 10. So A minus 10 is 0. So you are left with 5 plus 3. That is 8. So, but that is a nice way of programmatically doing it. Once you write software, the machine code actually looks like this, and this is how the machine code is executed in the CPU. Okay, so we can just try this out, the rest of the code. So now currently the accumulator contains the value 18 or 12 in hexadecimal. Now I am going to perform this operation of 4D, which is going to take away 6 from it. Okay, so let me execute. Keep on executing. You can just keep an eye on the entire system. So 6 is now loaded to register B. Now the value is going to be taken away. The accumulator will now contain a different value. So this is going to contain how much? 18 minus 6, which is 12 in hexadecimal or C in decimal. C in hexadecimal. Okay, so C. Again a display. I'll do a display. Now my display contains C. Okay, display contains C. So that part is also over. Now I am going to do the execution of 4E. 4E is basically again going to take out the value 4 from C. Okay, the answer is going to be 8. So now 4 is loaded. So C minus 4 is going to be the final operation. So you can see the result here, 8. It is yet to come to the display. Now it contains the value 8. Okay. So this is what, this is how we should implement this kind of operations, right? So if I want to do it, let's say in a loop, right? After this value 70 is displayed, we should ideally go back and go back to the 0th location, right? So I want to jump. So I can also use this value 6 to jump to the initial value. So here I can write 60. What is 60? 60 is again going to load the accumulator this is basically going to go to this program instruction called 1A. Okay, so we can try this out. So it is now executing 6.0. See, instead of going to 0.5, because it doesn't know, the processor doesn't know what is data and what is a program, right? So after 6.0, it did not go to 0.5 anymore, right? Rather, the program counter got reset to the value 0. Okay, so this is what is kind of interesting. We have implemented even a loop, right? So we are trying to do this, right? Say this arithmetic computation, some plus, minus and all. And once I am done, I am again going to redo this computation. So if I start doing it automatically, because that is what the processor does, because if there could be some other, let's say some other mechanism in which we update the memory, let's say this is a sensor value and I want to do this computation, and the sensor automatically updates the memory, right? In that case, the processor does some computation on those sensor data outputs in an infinite loop, right? So now if you can simulate that, right, it is going to run much faster, right? Once I start the, let's say, the clock, right, I am running the clock in this simulator at 100 milliseconds, right, 100 millisecond time period. So this is like a 10 hertz clock. So now you can see that it is going to be very, very quick, right? So 12, after 12 it is C, after that it is going to be 8, and after 8 again it is going to go back to the value 8, because 5 plus 3 was 8. So it is much faster, and it is an automatically looping through the entire program, right? I have adding this 3 numbers and subtracting 2 numbers and doing that in an infinite loop, right? So as you can see on the left hand side, the controller is continuously pumping the control signals to the processor. Okay, and this entire thing is automated. Okay, there is nothing other than, if you want to do a system reset, that is different. So it is going to completely halt the system, and typically all this execution of the program, starting of the program and the stopping of the program and releasing the memory and so on are handled by the operating system. In case we do not have an operating system, we have to do it in some other way. Maybe you can have a hardware reset where we manually stop the program and manually start the program. In our case, that's why I have a button called a system reset. You can see there is a system reset button, and this button can be used to reset the address, reset the program counter, as well as the reset the C state counter. At any point of time, I can do the system reset. It is going to completely halt everything, because if it is 1, everything is reset and then is going to be held like that. Once I make it 0, and it is going to again start from the beginning. Okay, so this is, I think, giving you an idea of how this end-to-end computation happens, right? And you kind of know the internal details of all of them, right? But this is an intro to the end-to-end system, right? Now I am going to go to each one of this component and going to show you how it is implemented, so that you can also implement something close to this yourself, right? I have shown you the registers already. I have shown you the ALU already. The status register I am going to show you, but it is a very, it's nothing different other than the fact that this is just a 4-bit register instead of a 8-bit register, right? This is the memory. There is nothing that I have implemented here other than just borrowing this component from the simulator. Program counter is a 4-bit counter, right? And that has a facility for loading and being reset and incrementing, right? So these are the control lines you have to now. So I'll stop the simulation clock and let us concentrate on each one of these components. So if you look at program counter PC, the program counter has these lines, right? One is this reset, right? So this is the reset that could be resetting the program counter. There is a clock input. The clock input is of course required. There is an enable, right? If you disable the PC, it is not going to write to the output, right? If the enable is on, only in that case PC is going to write to out. This out is this counter value which goes to the bus. So this out is actually the address. Okay, so the PC contains the address, but the PC has to communicate this address to the bus, right? Otherwise, how it will do that? So the out is basically going to be connected to the bus, as you can see, the blue line. If enable is equal to 1, only then, otherwise it will not write anything, because it is going to hamper the data communication that is going on among other components in the bus. So only when PC is allowed to write to the bus, it will write, otherwise no. And for that, the PC out signal has to be high. So the PC out in the controller is going to be linked to the enable input of the PC. Okay. Similarly, you also have load. If there is a jump instruction, for example, so the PC has to be loaded by a value. So if I, instead of doing 60 here, if I did 61, right, I can try out and show you. After it reaches this point, right, it is not going to go to 1A, it is going to go to 3B. Okay, and you can see that, right? Instead of that, if I just simply use 61, it is not going to go to 0, 0. So 1A is not going to execute, it is going to be executing 3B. Okay, and the result might be different, because your result contains 8 at this point of time. When the computer program finishes, when it is at the jump instruction, the accumulator contains how much? Accumulator contains 8. If you do 3B, B contains how much? 3, right? So 8 plus 3 is going to be 11, right? So 11 is B, right? So you can just check that, right? If I just do 61, how the program execution changes. So let us restart the program and see what happens, right? Just for fun. Let me let me reset the system clock. So this starts the clock, right? And then I'll reset it, right? So it will, let us do the entire cycle. So 8, let us see, let us follow this. After 61, I think if you have seen, it has gone to B, right? It has basically shown B. So you can see the compute cycle has changed. Okay, so this is completely different, because they are going through a very, very different cycle, right? So if you follow the jump instruction very carefully, after it reaches 61, it will go to the first location. See, so if I want this guy to jump to this fourth location, let's say 3C, so 0, 1, 2, 3, I want to write here 63. So once it comes to 63 or this location, it will go here. See, it has gone from 63, it has gone here. It's a jump instruction. So what is happening in this case, right? This value 63, the 3 is going to be loaded to the program counter. Okay, so the program counter, whenever there is this jump instruction, you can see the load is going to be high whenever the jump is going to happen. Okay, so whenever the jump happens, so there is a one point of time load was high, and at that time the PC got loaded with the value 3, and from there the execution continues. So these are the 3 control inputs that are needed. One is INC. INC will always be needed whenever you are going to the next instruction. Here you see that INC, one point of time it is on and then it is off for some time. This is on because the next instruction is going to be starting to execute. Rest of the time, it is the rest of the clocks, it is not going to execute. Okay, so if you look at a micro instruction sequence, we might have 5 micro instructions, and out of those 5 micro instructions, only one micro instruction is going to increment the PC. Rest are not going to increment the PC. So if you look at the clock, maybe there are 5 clocks, but out of 5 clocks, only once INC is going to go up. Okay, because this is going to fetch the next instruction and PC has to be incremented. If there is a jump only, then the load will be high, otherwise not. And again, enable PC will only be high if for fetch, right? Whenever I am going to load the PC or take the value from the PC and load the memory address register, that is only once per instruction. Otherwise, I won't touch the PC. Okay, so enable and INC are going to be used only once in an instruction, and load is going to be used if I am using jump, otherwise not. Okay, so this is the only thing that we have to say about PC. And if we look at the PC, this is a circuit that is available in any textbook, right? And you can always come up with your own circuit. This is a circuit, I think, that is there in Malvino's book or even in Morris Mano. So this is a counter with D flip-flops. So these are the 4 D flip-flops, right? And these 4 D flip-flops are basically the 4 bits of your counter, right? On the right hand side, I have the counter enable because I need to have a tri-state buffer to allow the counter output to the bus. Otherwise, there cannot be any output. So if I make the enable 0, you can see that everything becomes high impedance. So there is no output from the counter to the bus. Only if enable is 1, there is an output. Okay, so that is one thing. Reset is going to reset the value of the counter. Load an INC, right? If there is an INC is just if INC is 0, even if you put a clock, there is nothing going to happen. Okay, only if INC is enabled and then you put a clock, you can see the count is starting to get incremented. So 5 and so on. Okay, so you can just follow this value. If I put a clock, it basically counts. Okay, so the other thing that also has to be looked at is the reset, right? If I push reset, it basically asynchronously resets the value of the counter. Okay, so this is a reset that I was using for the system reset. So if I click on reset, the program counter directly goes to 0. Okay, the other feature was load, right? So if I do not use increment, and let's say I want to load the value, some value, right? So of course this should not be 8 bits, right? Here the bus was 8 bits, but I'm ignoring the top 4 bits, so it doesn't matter what you put, right? Even if I put 0 or 1, it doesn't matter. So I want to, let's say, load this value with 9. So I put the last 4 bits as 9. Okay, so the expectation is that the program counter is going to be loaded with the value 9. Okay, so I can make this load is equal to high. INC is 0 because I'm not incrementing it, right? Because if I do increment, this is basically 0 plus 1 is 1. So if I put a clock, you can see that the counter is now loaded with the value 9. Now I will I'll just put the load to 0 and put this increment high. So now it will go on to the path of regular counting. So it will become 10. It will become 10, 11 and so on, right? So this is a very, very important feature to implement jump instructions, anything related to jump or flow of the program, right? So the program counter needs to be loaded by an external address. So the external address is basically issued from the instruction itself because the instruction contains jump. So the part of the instruction is going to tell that, hey, please go to this 9th location. So the 9 is going to be issued to the bus, and the bus is going to be read from this part, right, address. And if you look at the processor, the PC is basically having an input. So if you follow the blue line again, the blue line is basically connected from the bus to the PC's input address. Okay, so I am just putting the top 4 bits as 0 because this is ignored anyway. Okay, the top 4 bits are 0 and the bottom 4 bits are the actual value that we are interested in. Why it is 4 bits? Because we are only dealing with a 16-byte memory. Okay, it's very, very small memory, which probably does not make any sense for a real computer, but this is just for a conceptual understanding of how this entire thing works. Okay, so this is about the program counter, and we will look into the other 2 components, which is kind of important, is the memory address register and the instruction register. So MAR and instruction register, and how they are playing a role in getting the instruction executed and what they contains.